Hello. So in this video we are going to look at a summary of some digital filter design techniques. So this is going to be a whirlwind summary and we are not going to cover all aspects. I will focus on the FIR filter design though, that too from an implementation perspective. Okay, so let's first look at how you can design digital filters. The importance of digital filters stems from the fact that in many of the applications that we consider, we need to process these signals. Process implies that we can typically consider boosting or suppressing frequencies. So if you now take the example of an audio equalizer, you have seen that if you increase the bass, then the drums and other instruments seem more pronounced, but if you increase the treble, other instruments or voice seem more pronounced. These kinds of changes in the signals to remove noise, to amplify certain sections becomes very, very important, not only in the context of audio, but in every application, including communication or medical signal processing and all of those. So to summarize how we can look at filter design in the digital domain, there is a significant difference from what you would do if you were to consider this in the analog domain. So let's first look at what the problem is. The problem is this. Put this straight. Okay. So we have, let's say, this is basically minus pi, this is pi, and we desire a filter, let's say, which has something like this. Okay. It has basically a pass band over here, let's say between let's say omega 1 and omega 2, and it has stop band over here. Okay, that means that you want the gain to be 1. So let's say this is our h of e per j omega. You want it to pass all frequencies between omega 1 and omega 2, and let's say you want it to not pass any of the signals between 0 and omega 1 and omega 2 and pi. Of course, assuming things are real, there will be a symmetric thing on the left and ignoring that. This basically means that you have an abrupt jump over here, and you have an abrupt jump over here as well. Now, as we have seen in practice, abrupt jumps are never admissible. Since abrupt jumps are never admissible, we always have a gradual kind of it's always gradual, and this gradual means that there is actually what is called a transition band. So first of all, what are the parameters that we are interested in? The first is we are actually interested in the pass band, that is what frequencies are you going to allow through. Stop band, that is what frequencies are you going to absolutely prevent from going through. Next, we have what is called a transition band. The transition band is because, as you know, whenever you have filters which have a rectangular shape or abrupt jumps in the frequency domain, those filters are not possible to realize using finite coefficients. A standard example being the ideal low pass filter, which is sin omega c by n by n, sin omega c n by pi n, and there is no either FIR implementation or a realizable recursive implementation. So this is one, but then there is also some other aspects. There's basically, when you can't really have things absolutely flat, because you know that the DTFT is usually continuous and has some nice properties to it, and it's actually impossible to have it to be an exactly flat line, because it will become like there will be issues with regard to its continuity, differentiability, and all those. So typically there is also a slight variation here. So there is also pass band and pass band ripple, because you want the gain to be 1, but the gain will always hover around 1. It will be 1.01, 0.99 and things like that. Similarly, even in the stop band, there may be those kinds of aberrations. So we will take the peak of the stop band and call it stop band, and it's called stop band suppression. So what I have drawn is something like a band pass filter, but of course these things can be extended to all of those. So now once you are familiar with these terms, so we have the pass band and the pass band ripple, the transition band and the stop band suppression. The aim is for you to design a filter which is to specification. So all of these form part of the specification. Now if you start demanding a higher and higher parameter, for example, I want small stop band, small pass band ripple, high stop band suppression and things like that, then it will turn out that the complexity of the filter starts becoming more and more, as we shall see. Okay, so let's, I think this part is clear. So one way to construct filters is to directly use continuous time filters. Continuous time filters, and you can then either sample the impulse response or use what is called the bilinear transformation. Okay, so this is something, these are two approaches. Over here what you have is, if Hc of t is the impulse response of a known continuous time filter which actually does a good job, then you can actually write Hn to be NTD. In fact, you can add a TD scaling just for ensuring that the gain properties are preserved. So TD Hc of NTD, this is called the impulse invariance method. So this is the impulse invariance method. Here the impulse response of the filter is directly sampled. Now as you have seen in the context of sampling theorem, you can sample an impulse response absolutely accurately only if the signal is band limited. But of course you know that if the impulse response is band limited, that impulse response corresponds to a filter that is band limited, then you need to sample it more than twice the that to ensure the Nyquist criterion is satisfied, and all those things come in. In fact, a significant limitation of the impulse invariance method is that it works only for low pass and band pass filters, because for high pass filters you get aliasing. So I am not going to focus too much on this, but this is a good way to get a simple, suppose you have a good Butterworth or Chebyshev or continuous time filter. You can actually just use the sampling approach to get a discrete time filter. For example, let's take a simple example. If suppose that we take e power minus t u of t is your Hc of t. So suppose this is just one of the low pass filters. Now notice that this Td is a parameter here. This is not a band limited signal, but Td is a parameter here. So if you now take Hn to be equal to, it will be Td into e power minus NTD u of t. Okay. So this actually turns out to be of the form, in fact if I ignore this Td for now, it's just a constant, you just this is actually u of NTD rather. This is going to be a power n u of n. So it's a complex exponential. So this basically, when I say complex exponential, it's exponential. So e power minus NTD directly gets a power n un. But now what is the cutoff? So here your choice of TD is going to matter. If you choose TD to be small, you're going to get a filter which samples a lot of the, it's going to sample a lot of the TD value, a lot of e power minus t. But if you choose a TD that is large, it won't sample. So you can basically make a simple example. So for example, let's say that we'll go from 0 to 10 and we'll go step 0.1, and then let's actually look at I will just plot e power n, e power minus n. I'll just plot e power minus n td. Let's say td is equal to 1, and I'm just going to plot, td is actually 0.1 because I've chosen just 0.1 over here. And if I just plot this, in fact, let me do a stem to emphasize that this is just a, okay, and then show. Oh, sorry, of course, minus. There's a minus over here. You can see that it samples the e power minus t very accurately. But suppose you choose a very coarse sampling, like td is equal to 1 second, you will get this. How does this reflect in the frequency domain? That is something you can just use FREQZ to check out yourself. Okay, there's a trade-off. If you choose td to be small, you need more and more samples to get the filter represented accurately. If you choose td to be large, then you may not get the frequency characteristics accurately. The other approach is the bilinear transform. The bilinear transform is not very, it's not very difficult, but it's a very neat technique. Basically, suppose you have the Laplace transform of a continuous time filter, let's say HC of S. Then what you do is you replace S with 2 upon Td, 1 minus Z inverse upon 1 plus Z inverse. So if you basically just say H of Z is HC of 2 upon Td, and I just multiply by Z, Z minus 1 by Z plus 1. The claim is that this is a usable continuous discrete time filter. How? So it turns out that this bilinear transform does an interesting operation. If you have, okay, let me now do this carefully. If you have this S plane, what the bilinear transform does is, it takes the left half plane and then just converts it to the unit circle, and the right half plane is outside the unit circle. So it's almost like what you're doing is you are pulling the left half plane and bending it around to make it into the unit circle, and then the rest of the space becomes the right half plane. In fact, if there are any poles in the left half plane, you know that corresponds to stable filters, right? Similarly, you can see that those poles will have been exactly mapped to be within the unit circle. So that, it turns out, is an interesting operation. In fact, you can very easily see that this transformation maps the imaginary axis to the unit circle. How? What is the unit circle in this transformation? The unit circle is where Z is equal to e power j omega. So what happens if you look at 2 upon Td, Z minus 1 upon Z plus 1, that turns out to be 2 upon Td, okay, e power j omega minus 1 by e power j omega plus 1, and this, you know that whenever we have this, we can take e power minus j omega by 2 out on both the numerator and denominator, and we have, this is j2 sine omega by 2, and this is j2, sorry, not j2, 2 cos omega by 2, and this gives me j2 upon Td tan omega by 2, where omega is a number between minus pi and pi. So it maps, so this mapping omega by 2, if you take all numbers between minus pi and pi, you get all numbers between minus infinity and infinity. So this is actually purely imaginary, which means this has to be j omega, where this omega is the imaginary part of S. So this maps the imaginary axis to the unit circle, and anything to the left of the imaginary axis to within the unit circle, the unit disk, so to speak. So this is an interesting transformation, but notice that if you look at the correspondence between frequencies, you have 2 upon Td tan omega by 2 is equal to omega. So this is the continuous time omega, which is 2 pi f, and this is the discrete time omega, which is between minus pi and pi. Notice that there is a Td here. Now it is tempting to think that this Td has something to do with sampling. It does not. it actually controls this nonlinear warping. That is, tan omega by 2 is a function which maps a finite length interval minus pi to pi to minus infinity to infinity. How exactly that happens is controlled by tan omega, controlled by this TD. So you can actually look at this mapping carefully and try to understand the changing TD changes the filter. I urge you to check out in SciPy. If you look at SciPy.signal, they have the bilinear. Okay, they have the bilinear transformation, so you don't have to really sit and substitute this z minus 1 by z plus 1 and things like that. You can actually just plug in the correct values and it will do the job for you. Okay, so in fact, the filter design tools in SciPy, for example, if you look at the Butterworth, they actually do digital filters directly. So they do this substitution for you. So you don't need to manually construct a continuous time filter. You can directly get the discrete time filter by using these tools. Of course, if you have access to the design of a continuous time filter or a continuous time filter design tool, then you can use the bilinear transform to perform the transformation. Okay, so this was my summary of the filter design. When you talk about IIR like filters and use the impulse invariance to make the comparison. Now the rest of my focus will be on FIR filters. Now FIR filters are a little more interesting because we get certain things for free. For example, FIR filters are always stable, okay, because they are by design absolutely summable because all the values are finite, you can sum them. And we can, as we will see, we can design linear phase filters easily. So why is this linear phase important? So as you have seen in some previous videos, this linear phase essentially preserves, it basically delays all frequencies by the same amount and therefore avoids the introduction of any additional distortion. The additional distortion is something which can come up and hurt you very seriously. Why, but if you have a linear phase filter, you can avoid that to a significant degree. Okay. Let's have a look at how you can get FIR filters. So when I talk about FIR filters, always you have something like, see, this template is always needed. What is this template? See, let's say I need a low pass filter. If I need a low pass filter, then I always am going to say, okay, let's start with, I need a low pass filter with cutoff omega c. Okay. Okay, so let's make it nice. Okay, so this is my low pass filter with gain 1, okay, and you all know that the impulse response of this is sin omega cn by pi n, which is unrealizable, and I want an FIR realization. Okay, so if I want an FIR realization, here is one way that I can do it. I can do sin omega cn by pi n and multiply it by a window, okay, and of course if I want it to be causal also, that is also something useful, especially when you are doing some real-time processing. You can also add a delay, and let's say that the window is accounting for the delay. What does this mean? You've already done this, because what do you do when you want when you just restrict the values of n for which this is defined? You are actually using what is called a rectangular window. So what does this rectangular window do? The rectangular window has this distinct disadvantage of being very simple, but the distinct disadvantage that in the frequency domain you are now going to convolve it with, and remember, if you are doing a rectangular window, you are going to convolve it with that sin m omega by 2 by sin omega by 2. So it's like you are convolving it with a sink, and that is what is going to result in something like this. You remember you have this kind of you have always this kind of thing. So instead of speculating, I can always just see. So here's what I'm talking about. So you all know that we can do. So you know that we can let me take n to be np dot a range. Let's say minus 49 to 50. That's minus 49 to 49, and then I'm just going to say h is equal to sine. I'll say omega c is pi by 2. Okay, np dot sine, of course. This is divide by 0. Okay, because at the midpoint, at the HC of 49, they're not a number. We're going to make this sine omega c by pi, so that's 0.5. So now if I do now plot W, and then I'm going to take 20 into np dot log 10. Then I want a dV plot, abs of h, and show. Okay, let me also add a grid. So you can now see that if I zoom in, let me zoom into this part alone. You can see that you want it to be ideal, but there are ripples here and there's these big ripples here, and the suppression is like, what is the suppression? Over here you can see that first of all there's a transition band, because pi by 2 is 1.57. It doesn't really fall off at 1.57. In fact, it does something like this. Okay, it starts falling around 1.55, keeps falling till 1.6, and then rises again, and there's this side lobe. Okay, now why does this happen? This has happened because you are convolving the rectangle with the sine m omega by 2 by sine omega by 2, which is the dTft of the rectangle. This is causing this issue. One way to make it slightly better is, or potentially better, is you can of course increase the, we can make it 499, 500, and it is equal to this, and instead of h 499. Okay, now again I will make it to the final set. Okay, so now there is maybe some slightly better suppression and everything, right? So if you zoom into this area, you see that the ripples are really tiny. Okay, the ripples are really tiny, but in fact I need to take FREQZ with a larger n. I just do that for you. So I think n should be more than 512. So yeah, now you can see that the ripples are much smaller. Okay, they are there, but they are still, because of the Gibbs phenomenon, they will always be there. They are much smaller. But over here you can see the suppression doesn't improve at all. The suppression is always minus 21 dB. Okay, so the suppression is always 21 dB. It doesn't improve at all. So increasing it doesn't improve the suppression at all. Okay, so in this context is where it is actually slightly better to look at other windows. So there are actually a host of other windows which one can try. So this windowing is not restricted to the windowing is not restricted to rectangular window. We can take other windows. So I'll give you some examples. Okay, for example, you can look at the hand window. Okay, this hand window or Hanning window is something which is really it's simple to implement. It's actually Wn is equal to half minus half cos 2 pi n upon m 0 less than equal to n less than equal to m 0 else. Okay, so what is the difference between this and the rectangular window? So if you notice, see again, this starts when you put n as 0, you get 0. When you put n as m, you get 0 again. But when you put n as m by 2, then at that time the cos becomes cos of pi, which is plus 1, and you get to 1. So this is actually something which rises and falls. Rather than speculate, why not just look at it? So rather than me sit and write this, I'm just going to say scipy dot signal. Okay, look at scipy dot signal dot hand. You just need to give m. Let's say 10. They give me some numbers. I'll do stem. Okay, this looks like a cos. Let me do 100. It looks like a nice cosine, which is exactly what it is. Now, the purported theory is that this is a better window. Okay. Now, why is it better? Let's actually look at the frequency characteristics of this. Okay. I'm going to give you the frequency characteristic of this window. Now, if you look at this window actually, I have to zoom in over here. Ignore the amplification, anyway, it doesn't make much sense. This starts at around, let's say, 34 dB, and the first lobe is at around 2.5. So it gives you about 32 dB of suppression, supposedly, which means that instead of doing what I did earlier, if I now do this, so if you remember, our H was there, which is the low pass filter, right? Now, this was 999. Now, if I say scipy dot signal dot hand and say 999, okay. Now, if I now look at the frequency characteristics of my filter, okay, I am going to do 999 multiply by H. So this is actually supposedly a low pass filter, but the low pass filter is does not use a rectangular window, it uses a hand window. Let's check what I get. Now let's look at the magnitude response. You should be able to see that in the magnitude response that the transition band is slightly higher, okay, but the suppression now, if you see, you start at 0 dB, the suppression is now about 43 dB. It's much better. There's a bigger transition band though, because if you now rewind this video and check what you had in the earlier case, the transition band would have been slightly different, slightly narrower. Here, it's actually, look at it, it gives you excellent performance because you get this kind of a suppression. Okay. Okay. What are the other windows? So there's this another simpler window, for example, Bartlett. The Bartlett window, as a simple definition, the Bartlett window is basically like a triangular window. It's 2n upon m, 0 less than equal to n less than equal to m by 2 for m even, and of course 2 minus 2n upon m by 2 less than n less than equal to m. So m has to be an even number, 0x. This is actually a triangular window. So if you see, it's a triangular window, and if I try doing 101, also it gives me, but there will be an extra point, so it's better to do. I'll just show you what happens. It basically is going to just give you an extra point. That's actually okay. You can just look at the help. Okay, so it's just that the endpoints are at 0. Okay, so now if you're going to use, if you now use this, okay, here. Now, so with the Bartlett window, notice that you get something which is exceedingly good. Okay, in fact, maybe Reason I have this is because I've chosen a large N. I'll go back to the smaller filter, or no, let's stick with this. So you can see that the suppression is actually very good. You can see that it starts going down at around 1.55 and then it goes down and goes down, it goes down. You can call this the first peak, let's say, it's like at minus 27, but then there are no other side lobes. It doesn't keep jumping up and down like the rectangular window did. So in that sense, this is actually very good because it just keeps going down almost monotonically, not exactly, but almost monotonically. You can see that, you know, it's like it does go. So this gives you an even more, even better performance. But then there is a price you pay. The price you pay is that it goes down really slowly. For example, 1.65, you got to for minus 43 dB suppression at a much faster rate in the hand window. Here, maybe not the case. Let's look at the Hamming window. These are all, basically using the fact that if you use a better window than the rectangular window in terms of the frequency content, you will get better performance. This is a slight variation of the hand window, 0.54 minus 0.46 cos 2 pi n upon m, 0 less than equal to n less than equal to m, 0 else. So this actually is just a slight perturbation of this hand window. Okay, we will just see what happens. So in the Hamming window, look at the performance over here. First of all, in the passband, the ripple is almost gone. The ripple is almost gone. Okay, the ripple is like nearly gone. Of course, I need to not do this. I need to do something like this for you to see the ripple. Okay, you can see the ripple slightly over here, but it's very, very muted. And what happens for the transition band? It starts transitioning around 1.56 and it stops, the transition ends roughly around 1.58, not bad. The suppression is excellent. The suppression is around minus 54 dB, which is fantastic, right? So you get excellent suppression. Now what? Now this is not too bad, it's very interesting because you are just able to replace the rectangular window with a window which has better frequency characteristics and get such excellent performance. Okay, I just do one more called Blackman. By the way, it is not mandatory to memorize these. These can be found in reference books. Okay, the Blackman window is also again in the same family. Okay, so it's 0.42 minus 0.5 cos 2 pi n upon m, and then plus 0.08 cos 4 pi n upon m, and 0 else. Okay, so the Blackman window, it's again just very related to these Hamming windows and all those. So we'll just do that also and see what we get. Again, not very, somewhat close to what you saw in the Hamming and Hanning windows. Suppression of I think the transition band is slightly higher. It's again 1.56 to about 1.59. Suppression of about minus 75 dB, which is fantastic. So you get excellent suppression, excellent performance by using these windows. So this is actually a good way to take a template filter with like an ideal low pass filter. You can even repeat this for ideal band pass and things like that. And you can directly apply these windows to get slightly better performance. Now, one thing is that if the original filter was linear phase and then you can use these to get linear phase filter, that is a good thing. But it may be a good idea for us to design a linear phase filter with certain targets. For example, I'll show you. So you all know that when there are actually, if you there are these type 1, type 2, type 3, type 4 linear phase filters. These type 1, type 2, type 3, type 4 linear phase filters have this nice property that they are linear phase guaranteed. They delay all frequencies by the same amount. Only the amplitudes are amplified or muted. So now, if you have this linear phase filter, can we directly design these linear phase filters is a question which we should ask. So for that, there's basically the equiripple FIR filter design, okay, using the Remis algorithm. Okay, actually this Remis is actually a Chebyshev optimization based approach. So the Chebyshev optimization means that it's actually so what you can think of it is that they basically formulate an optimization problem, and this optimization problem is solved for you to get the best filter. And the equiripple is because the ripple is actually equivalent in both the pass band and the stop band. So this is basically the detail of what this is. Now I am not going into the details of what the exact methodology of the algorithm is. This can be found in textbooks like Oppenheim and Schaffer. And this optimization algorithm and these kinds of the algorithm, if you want to learn more, is basically you can look at the so-called Parks McClellan algorithm. This this came about in the 80s, and you can just look at the references which propose this. Okay, it's actually a Chebyshev polynomial based approach. So Chebyshev polynomial is basically a cos of cos inverse, and you can get some nice optimization properties therein. But the key thing is that they allow you to do equiripple FIR filter design which have guaranteed linear phase. Okay. Again, like I told you, for this part also, we are going to do it using a practical approach. So from the scipy.signal, I am going to import the Remis function. This Remis is actually again the name of a mathematician who will develop this, called the Remis exchange algorithm. It's very related to the so-called Parks-McClellan algorithm. It calculates the FIR filter impulse response, whose transfer function minimizes the maximum error between the desired gain and the realized gain in a specified frequency band. Okay, this is not too difficult. What they're saying is that this is the desired gain in the pass band, desired gain in the stop band. Okay, this will minimize the gap, the deviation from these. Okay, so let's check what we need. We need to provide the number of taps, the frequency bands, and the frequency bands must be specified as numbers between 0 and in terms of fs. So it must be given as a number between 0 and half, and desired. Desired means that it's the desired response that you need. Let's try. I want a low pass filter. Let's say I want a low pass filter, and let's say I want these properties. Okay. So I want a low pass filter. Okay, I'll draw only one side. Okay, 0 is pi. I want a low pass filter which has cutoff at pi by 4. That's all. I want a low pass filter is cutoff at pi by 4. Okay. So what do we need to do? We need to say h is equal to Remis, and let's say I give 20 taps. Okay, 20 taps, low pass filter. Okay, now if you remember, we need to give bands and desired. Okay, the bands are 0, and I need to give it in terms of pi. So pi by 4 will correspond to, so let's see, 2 pi corresponds to fs, pi corresponds to 0.5, so pi by 4 should correspond to 0.125. Okay, but I need to give a transition band, so I'll go from 0.12 to 0.13 and then I'll go up to 0.5 and the desired values are 1 and 0. What does this mean? Between 0 and 0.12, take it as 1. Between 0.13 and 0.5, take it as 0. Okay. Let's study the properties of this filter. Let me write it in line so that I can quickly keep iterating. Let's pylab dot plot. I think I will do W20 into NP dot log 10 abs of H. Pylab dot show. Okay, obviously I made a mistake. So let's see. Again, I'll say WH, even FR equals Z of H. Okay, this part is okay. I'll say pylab dot plot W20 into NP dot log 10 abs of H pylab dot show. Okay, I think I made a mistake over here. Okay, we'll focus on this in a minute. So I need to, I want to also view the phase response in the same plot. So I am going to use subfigures for this. Subplot. I think I'll call this 1, 1, 2. Sorry. 1, 1, 1. Okay. So I think I will do, I'll call this 2, 1, 1, yes, and then I'm going to say, I also need a grid over here, okay, grid, and then I'm going to plot the phase. So I'm going to say pylab dot plot, pylab dot subplot, 2, 1, 2, pylab dot plot W NP dot angle H. Yeah, I think this is fine. I need the grid for the phase also. Yeah. Okay. Okay, so this is what we get. It's first of all we can see that it's generalized linear phase. That's very clear because you know, wherever it crosses 0 you have jumps of pi, which basically corresponds to a sign change, and wherever it has you know, 2 pi jumps, we don't really care too much about it. It's all linear otherwise. So we get guaranteed linear phase, but the performance over here is really poor. Look at the transition band on, you know, pi by 4 corresponds to 0.7. It's actually doing really badly. The reason is because the length we have chosen 20 is quite tiny. Let's actually choose the length as 100. Okay, you can now see that there are some ripples in the passband, ripples in the stop band. Notice the stop band suppression is actually really flat and good, because that's what equiripple means. The ripples are the same in both the stop and the transition band. Sorry, stop band and the pass band, and there's a transition. This is not too bad. Okay, let's start increasing the length a little bit. Now have a look at this. This actually did a great job. And there is a ripple still there. Okay, and this ripple is not going away. But this can be explained. Using the choice of the transition band. So we have chosen the transition band to be between. Between, let's say, just 0.12 to 0.13 corresponds. You can think of it as 0.12 into 2 pi to 0.13 into 2 pi. That is between 0.24 pi and 0.26 pi. I think that will work out to, just 1 second, 0.24, 0.26 pi is roughly, let's say, around 0.7. Yeah, this is the transition band. Let's actually do one thing. Let's go back to, let's maybe just choose the length of 100. Okay, this is the transition band. Let's actually increase the transition band. I'm going to go from 0.11 to 0.14. So if I make the transition band wider, notice that the ripples become almost indiscernible. The ripples are almost gone. Why? Because if I make the transition band wider, I'm able to get much less ripple. If I make the transition band narrower, for example, if I make it 124, 126, notice that the transition is really sharp, but there is huge amount of ripple. So there is a trade-off here directly. You have to be able to trade off between the transition band and the ripple. So this is an important thing to note in the Remis algorithm, the Parkes-McLaren algorithm. If you have a very narrow transition band, you cannot avoid ripples. Of course, you can always keep increasing the length. Okay, it will say fail to converge, so you can keep increasing the length if you want. It will become slightly better, but it increases the complexity. A better way would be to give a little more leeway, maybe not this much, maybe 118, 132. Even that reduces the ripple by a significant amount. Next, let's look at the stop band suppression. The stop band suppression over here is roughly around I think minus 31.1, minus 31.1, minus 31 dB. Okay, let's see how this affects it. If I make it 0.11 to 0.14, notice that the suppression jumps to about almost minus 56 dB. What happens if I increase the length? It becomes minus 100 dB. So increasing the length, let's go back to the original case. Let's say I wanted 0.125, so 0.12 to 0.13 for 200. So we have about minus 40 dB of suppression. So let's say I double the length to 400. This goes to minus 73. So indeed, increasing the length increases the suppression, and increasing the stop band, increasing the transition band. Like for example, if I instead do another minus 0.02 here, plus 0.02 here, yeah, okay, converge. Actually, okay, so let me give you a slightly 117, 3. You can see that the transition band becomes insanely good. It's like it suppresses it by about minus 110 dB or something. This is a really, really good performance. So this, of course, you don't want to have such a large length, because the number of calculations that you have to do to implement this convolution also starts rising as this length increases. So this Remis, or in MATLAB, and you can use the FIRPM function, is really, really powerful and can allow you to make linear phase filters which have excellent performance, very useful for audio, very useful for many communication applications also, because of their proper linear phase properties. Okay. One final thing is the Kaiser window. The Kaiser window is actually another interesting tool. The Kaiser window is basically like a generic window design. Okay, so basically it's like this. Instead of using a hand window, Hamming window, suppose you want to design your own window with certain specifications. You can use the so-called Kaiser window to design a filter that fits a certain description that you want. For example, if you want more suppression but the ripple is okay, or things like that, all these things, there's a generic approach. For Kaiser window, you can actually use the Kaiser odd and Kaiser functions. Okay, so these are present in your SciPy signal also. Kaiser odd and along with Kaiser functions. And since I am not going to cover this as part of this class, I urge you to look at Oppenheim plus Schaffer for a better description, for a more general filter window design tool. So that is something which you should look at. A warning I'd like to give you is that when you use Remis, be careful with this length. So if you, for example, if you say Remis, okay, let's say I'll say 10, no, let's say 50, 0, 0.12, 0.13, 0.5, and then I say here 1, let's say 0, 1. Okay, so and if I do, yeah, maybe I'll just do it over here. 50, and I'll just put this stuff over here. Okay. Okay. So now notice that even if I start putting, even if I put any length here, let's say 100, the performance is not going to be very good. The reason is because if you look at the length of H, it's 100. Okay, the length of H is 100. The other thing is, since this is a linear phase filter which is equiripple and things of that sort. Okay, let's maybe if you go back to your type 1, right? Type 1, right? Type 1 is basically Hn is equal to H. Okay, 100 length is type 2, I think. H, yeah, it's 100. So Hn, this is basically Hn is equal to Hm minus n. M is, because the total length is 100. Remember, M is odd. Okay, if M is odd, let's look at what happens if you sum H. Okay, it's something. What happens if you sum? Okay, let's look at H of 49, H of 50. It's the same. So if you actually now sum minus 1 power n into Hn, what will you get? So let's do. We have H, right? So I'm just going to do minus 1 power n into. So I'm just going to take np dot cos. So I'll say np dot r 0 to 100 into 2 into np dot pi to n. Okay, oops. Yeah, this. So if I now do H multiplied by this and np dot sum, it's 0. See, type 2 filters, basically filters that have an even length, have a 0 at pi, which means that you can never get a low pass filter using this equiripple filter design tool of length 100, which is why you get such an awful performance. Have a look at this now. Let me make the length 99. See the magic? So choosing the length is very important. Choosing length carefully is very important, because if we choose the wrong length, like for example, even if you increase the length to 200, you will not get a good filter at all. You must choose a length which is compatible. Okay, unless you choose a length that is compatible, you will not get the correct response. Similarly, if you want a low pass filter, okay, you can get low pass filters. Of course, you can get low pass filters to these lengths. That's not a problem. Okay, if you want to design specific filters like Hilbert transformers and differentiators and things like that, then you need to specify it carefully in the Remis function so that it will actually use the correct type. Okay, use the correct type and symmetry. That is something which you need not. I'm not going to cover now, but you can look at it. But this is something which you can look at. You should be very cognizant of the fact that this is something which is can affect your filter design. Okay, so don't choose lengths incorrectly. This is one of the very common mistakes which students make. Choose the length correctly. Okay, so this is what I had to say about filter design. You can practice the algorithms and just try to get a feel for how these work, and of course, and then you can use that for going ahead. Make sure you read the filter design chapter in Oppenheim and Schaeffer. Thank you.